Hey everyone, welcome back to compilersutra. In our last video, we explored the theory behind how C++ code get transformed into an executable binary, processing, compilation, assembly, and linking. Today we are rolling up our sleeves and doing this hands-on using C. Here is the simple C program we will be working with. We have defined a macro pi with a value 3.14. We calculate the area of a circle with radius 2. Instead of printing, we run the value, which we will inspect later. Before diving into each individually, let's see how to generate all intermediate files in one go using the -savetemp flag. When we use Clang with -savetemp flag, we see the test.i, s.s, test.o, and a.out. This test.i is a preprocessed output, test.s is the assembly code, test.o is object file, and a.out is the final executable. Now let's explore each of these stages step by step. Preprocessing handles macros expansion, file inclusion, and comment removal. So if you only want to see preprocessing stage, then we have to use Clang with -c flag. Let's peek inside. You will see what is showing on the screen. The macro pi has been replaced with 3.14 and all comments are stripped. Now let's come to the next stage. Next, the compiler translates this preprocessed C code into architecture-specific assembly. On my ARM-based Mac, here is what we get. But if you only want to generate the assembly, then we have to use Clang with -s flag. Here the fascinating ARM assembly we get. Sub SP has 16. Allocate 16 bytes on the stack. FMOV S0 hash 2.0. Loads float value 2.0 into register S0. The interesting part, loading pi value 3.14 through the multiple MOVK instruction. So here the instruction SCVT D1 SO convert float to double precision. FMULT DO D1 multiply pi into R and FCVT ZS W0 S0 convert float into integer or returning value. So why the complex pi loading? The compiler is constructing the floating point value 3.14 by building it pieces by pieces in register X8. Then move into floating point register D0. This is how ARM handles floating point construct. Once we have the assembler takes human-readable assembly and convert into a machine code, which is also known as object file. If we just want to generate this object file, we have to use Clang with -c flag. Now let's examine the object file. We will use the objdump tool with -d. It disassembles the object. So here, the left column shows hexadecimal machine code, what the CPU actually execute. The right column shows the ARM assembly mnemonic. This demonstrates how on high-level C code get translated to binary instruction. This file is not executable yet. It needs linking. So linking will combine our object file with necessary libraries like the C standard library to create a complete executable. Link the object file. If we are not giving any flag, it simply means that we are the want executable and it execute all these 4 pipeline together. Now we have a.out, a fully linked executable. So when we run a.out, no output appears. That's because we did not use printf. Instead, we return the value. In Unix like Linux, we can check the exit status of the last program using $? It will output 12. We calculated 3.14 cross 2.0 cross 2.0 is equal to 12.56. But main return an integer. So the float get truncated to 12. That's why the exit status is 12. Let's quickly recap the entire journey. Preprocessing, macros expansion, comments stripped, compilation, C code translate to the ARM assembly, and assembly convert to machine code, linking object file combined with libraries, and execution, program runs, return exit code. And that's a wrap. We have taken a deep dive into an entire compilation process from source code to executable using Clang on an ARM architecture. If you enjoyed this hands-on walkthrough, smash the like button and share it with your friend. If you have any questions, please comment below. Thank you.